Welcome to Chapter 13 of Surviving Statistics. In this chapter, we're going to discuss correlation and linear regression. We'll talk about the correlation coefficient, the regression equation, and multiple and single regression analysis. We began the discussion of correlation way back in Chapter 4 when we talked about a scatter plot. Now, the scatter plot that you see on the screen is the same one we introduced you to in Chapter 4, and a scatter plot shows us that there might be a possible relationship between two variables. In this case, we're talking about lemonade and how much lemonade we sold versus how high or hot the day was. And it looks like there might be some sort of a correlation. Well, in this chapter, we're going to learn to quantify that and compute numbers that'll tell us how strong the correlation is. We'll also be able to develop a regression equation that might allow us to predict how much lemonade, for instance, that we would sell based on what the projected temperature is for the day. When we're dealing with both correlation and regression, we're going to be dealing with two different kinds of variables, dependent and independent variables. Dependent variables, as the term implies, depend on something else, or at least that's what we're trying to determine. The independent variable is actually going to help us determine how much of the dependent variable we're going to have. So we designate the independent variables with X and the dependent variables with Y. So on the sample scale that you can see here, the lemonade sales, how much lemonade we sold, is going to be designated with the Y, and the temperature is going to be designated with X. And as we saw in that little scatter plot, there appeared to be some sort of a correlation between the temperature and how high the value of Y, or the lemonade sold, actually was. We measure the strength of the correlation with the correlation coefficient, which we designate as R. And R can range from -1 to +1, and we see that on the little illustration on the screen here. A -1 correlation coefficient would be a perfect negative correlation, and for every value of X that increased, Y would decrease exactly 1. And a +1 would be the opposite. For every increase in one value of X, Y would also increase one value. And of course, we're rarely going to see that in statistical analysis. And so we're going to be seeing strong negative and strong positive, moderate and weak correlations based on the value of R. And we'll learn to compute R right now. Well, here we see the formula to compute the correlation coefficient. It's not that difficult to see. We simply take the sum of X minus X bar multiplied by Y minus Y bar, the means for both X and Y. We divide that by n minus 1 multiplied by the standard deviations of both X and Y. Remember, X in this case is the temperature, and that is the independent variable. Y is the number of glasses sold of lemonade. That is the dependent variable, and we're trying to determine the correlation. So after we've done the calculations of X minus X bar, we've summed them up. We end up then, we've got the standard deviations with an R, a computed R, of 0.948. That indicates a very strong correlation or relationship between the high temperature and the number of glasses of lemonade that we've sold. The correlation coefficient that we just computed, 0.948, shows us that there is a very strong relationship, positive relationship, between the high temperature and the number of glasses of lemonade that we have sold. The regression equation allows us to attempt to predict how many glasses of lemonade we would sell based on the independent variables. So in this case, we see the regression equation formula as the predicted value of Y equals A plus BX. Now we'll go ahead and compute both the A and the B and predict a value here in the next slides. The slope designated with the B determines how much Y increases for every increase in X. Now, in order to solve for B, we have to have the correlation coefficient, which we already do. We also have to have the standard deviations for X and Y, which we already do. So to compute B, then, we can take the correlation coefficient of 0.948 and multiply that by the standard deviation of Y, 5.908, divided by the standard deviation of X, 2.248, and we end up then with a slope of 2.49145. Well, now we're ready to create the y-intercept. Remember from your line theory that the intercept is the value when x is 0. So the intercept, we have everything we need to compute that. The intercept is simply the y mean minus the slope times the x mean. So the values that we have are 49.857 for the y mean, the number of glasses sold. We also have the slope that we computed just a minute ago of 2.49145 times the mean for x of 70.857. We end up with a negative intercept of 126.68. So now that we have completed both the intercept and the slope, we actually have a completed regression equation. So the regression equation is the predicted value of y equals negative 126.68 plus 2.49145 times the value of x. So if the high temperature of the day is going to be 75, we could predict that Larry would sell 60.18 glasses of lemonade. And again, you see the math there, 126.687 plus 249 times 75 equals 60.18. Well, while we computed that regression equation manually, it's really not a fun thing to do, and of course Excel has a very easy way to do it. It also is in the data analysis. From the data analysis add-in, you would choose regression. After choosing regression from the data analysis tool, the next step is to highlight the ranges that contain your dependent variable, which is y, and the independent variable, which is x, and then you click OK. Well, here we see the output of Excel's regression feature. It gives us a little bit more information than we computed just a minute ago, but we do see that it did indeed compute the intercept in cell B17. We see the negative 126.670. The coefficient for x variable 1 is the slope of 2.491. We also see it computed the correlation coefficient of the multiple r of 0.948. Now you will notice perhaps some slight differences in the numbers for the slope and the intercept, and that's just due to rounding and how many digits we use versus how many Excel uses. The regression equation we just computed had only one independent variable. That was a single regression. Multiple regression is used to predict values of the dependent variable when we have multiple or potential multiple independent variables involved. Now here's an example of how we run a multiple regression. All right, we're back to Larry. Now, Larry thinks there might be other factors other than just temperature that are affecting how much lemonade he sells. For instance, he believes that he sells more lemonade when the humidity is higher. He also believes he sells less lemonade when it's likely to rain, and he thinks he sells more lemonade on work days than he does on the weekend. So he's going to create a multiple regression, and when he does that, he's going to throw every possible variable into the mix. Then, after he does the regression analysis, he's going to evaluate each possible independent variable and see whether or not it is a significant predictor for the dependent variable. Variables that are not significant predictors will be eliminated, and he'll run the regression again and come up with a very clean regression that will allow him to fairly accurately predict the independent variable. All right, so Larry collected a couple weeks worth of data. He tracked how many glasses of lemonade he sold. He tracked what the high temperature was that day, what the noon humidity was, what the chances of rain were, and whether or not it was a work day or a weekend. Now notice, for work day, that's actually a qualitative variable, but we're able to quantify it using something called a dummy variable. And so we'll use a 0 or a 1, and in this case we'll use a 1 for a work day and a 0 for not a work day. And that enables us to actually do regression based on qualitative variables. There are so many computations involved in doing multiple regression. I'm going to suggest strongly that you use a tool like Excel. So I'm going to step through doing multiple regression in Excel. So we've selected data analysis and then regression. Now we select the dependent variable, which is the Y range, and then we select all of the independent variables with the X range, and then we'll click OK and get our output. Well, here we see the result of the multiple regression. When you actually do a multiple regression, Excel will label your variables x variable 1 and variable 2. So I renamed them on the screen here so that we understand which ones we're working with: temperature, humidity, rain, and workday. So we have the intercept computed, and then we also have the slope for each of those other variables. So our predicted lemonade sales comes out to be negative 29.263 plus 1.205 of what the temperature is, plus 0.007 humidity, minus 0.235 rain, and minus 1.654 workday. Well, now let's go ahead and see how we would evaluate each of these variables to see whether all of them should be included in our multiple regression equation. All right, the first thing we evaluate in our multiple regression is the correlation coefficient, or R. Excel calls it multiple R, you will recall, but we see that it has computed a value of 0.976. That is a very strong positive correlation between all of the variables and how much lemonade we're going to sell. In our multiple regression, we threw every possible independent variable that we had in the mix, and we're now going to evaluate to see which of those really belong in the regression equation and which ones do not. So the correlation coefficient said that yes, there appears to be some significant predictors going on here, but the next thing we're going to look at is the global F test. That is part of the regression that Excel gave us in the output here, and what the F test is actually a hypothesis test that we'll go through, but it's answering whether or not any of these are really statistically significant predictors. Well, let me just kind of go over the fact here and see that we have a very high F computed. It's 0.45093. The significance, which is the p-value, is essentially 0. Well, right now I can tell you right now that there is at least one of these that is a significant predictor, but let's go ahead and step through the process here. The degrees of freedom are given to us as 4 and 9. So let's look at the table and see what the critical value of F at the 0.05 level of significance would actually be. All right, using the F table with the 0.025, remember it's a two-tailed test. We said 0.05 was our level of significance. With the degrees of freedom of 4 in the denominator and 9 in the numerator, we end up with a critical value of 4.718. So the official interpretation is, because the computed F statistic is 45.093, which is significantly larger than the critical value that we just looked up, we can determine that at least one of the independent variables is a significant predictor of the dependent variable. All right, we're continuing on with the evaluation process. We looked at the correlation coefficient. That told us, yes, there appears to be a strong relationship. We looked at the F test. The F test said, yes, at least one of the independent variables is a statistically significant predictor. The next step is to evaluate each and every one of those independent variables to see whether or not they are significant predictors. We once again do that with a hypothesis test. The null is that the slope is 0 and that it is not a significant predictor. The alternate is that the slope is not 0 and it is therefore a significant predictor. We'll also use the 0.05 level of significance with the t-test to evaluate each of these variables. All right, again, evaluating each and every independent variable to see whether or not it's a significant predictor, we're going to use the t-test. Our degrees of freedom are computed as 9. And so using the 0.05 level of significance with 9 degrees of freedom, the critical value of t that we're looking for is 1.833. Well, Excel did indeed compute the t-values for you. We'll see it on the screen here in just a second, but what we ended up with was temperature having a t-value of 2.4, humidity of 0.017, rain of -2532, and workday of 1550. All right, in evaluating each independent variable, we can see that with our t-test, only temperature and rain are significant predictors. Now, that doesn't mean that workday doesn't predict how much we're going to sell, but not at the 0.05 level of significance that we established. Now, notice also in the Excel output that we do have the t-stat, but it doesn't give us the critical value like some of the other data analysis features have, but it does give us the p-value. And so we can see in this case that if we're looking for the p-value of less than 0.05, we can see that again, only temperature and rain are significant predictors. So our next step is to actually run the multiple regression with just the significant variables. So here we see the result of the multiple regression with just the two independent variables that we decided were statistically significant predictors. Now you'll notice that the f-stat is significantly higher than what we ended up with before, but notice though that the multiple r, the correlation coefficient, is a little smaller. That's because the other variables did have some effect in how much lemonade we sold, but again, our criteria was 0.05 level of significance, and that's why we eliminated them, as they didn't pass that test. So here is our revised multiple regression equation with just the two statistically significant predictors. So we have predicted lemonade sales being negative 48.598 plus 1.461 times the temperature minus 0.217 the chance of rain. All right, here are some of the highlights from Chapter 13. We talked about dependent and independent variables. Dependent are what we're trying to predict based on the independent variables. Correlation coefficient, we saw the formula for that. It can range from -1 to +1 or somewhere in between, telling us how strong the correlation is between the independent and dependent variables. We were introduced to the regression equation, which includes the predicted value of y is the intercept plus the slope of the independent variable. We ended this chapter talking about multiple regression. In multiple regression, we throw in every possible independent variable into the mix and run the regression, and then we're going to figure out which ones are and which ones are not significant predictors. So we start, after we've run the regression, by looking at the correlation coefficient, the R, to see whether or not there is a strong enough relationship to continue. If there is, we look at the f-test. Remember, the f-test tells us whether or not all of the slopes are zero, or in layman's terms, are any of these significant predictors. Once we've done that and determined that at least one is a significant predictor, we look at each independent variable and we evaluate it with a t-test, or we can look at the p-value that Excel gives us. If they are significant predictors, we include them the next time we run the regression, and we'll create a more accurate multiple regression by just including the variables that were significant predictors. And remember, all of these lessons are based on my textbook, Surviving Statistics, which is available on Amazon. And do remember to check out my website for downloadable files, calculators, and other resources.